Welcome dear learners. We are continuing Unit 2 Chemical Bonding and Molecular Structure. In the present module, we are discussing dipole moment and its applications. This is the first part of the application. In this module, the contents we are discussing are dipole moment and percentage of ionic character, application of dipole moment with respect to the geometry of linear and bent molecules, illustrative examples. First of all, we are discussing about dipole moment. In the previous module, we just heard about the concept of dipole moment. The dipole moment is a concept which is used to represent the resultant polarity of a molecule. The concept of dipole moment was introduced by Peter Dipole, and the dipole moment is a vector quantity. The measurement of dipole moment enabled several applications. The applications include determination of geometry of molecules, determination of the percentage of ionic character, and it is also possible to determine the bond angle in the case of certain molecules. Now let us enter into more details of the concept of dipole moment. The degree of polarity of a molecule can be expressed in terms of dipole moment. The abbreviation of dipole moment is mu. It is the product of the magnitude of any one of the charge, that is either positive or negative charge, and the distance between them. Here, the magnitude of the charge either positive or negative means in a dipole, the magnitude of the positive charge is exactly opposite to that of the negative charge. Therefore, in measuring the dipole moment, we have to consider the magnitude of either the positive charge or the negative charge. So, this dipole moment being a vector quantity, and the direction of the vector is from positive center to negative center. That is, the dipole moment vector orients from positive to negative end of the dipole. This notation is used for showing dipole moment, and we are using an arrow with a crossed tail to represent dipole moment. So, this is the notation of the dipole moment, and its direction is from positive to negative direction. So, if we are taking HCl molecule and if we are representing its dipole moment, you can use this notation. Hydrogen is partial positive and chlorine is partial negative. So, this is the notation and direction of the dipole moment. Now, if Q is the charge at each end of the dipole and D is the distance between positive and negative center, theoretically this distance is equal to the bond length, then the dipole moment mu can be calculated, or mu is given by the expression mu is equal to Q into D. Remember, in this expression mu represents the dipole moment, Q represents the magnitude of any one of the charge, either the positive charge or the negative charge, and D represents the distance between the charges. Now, unit of dipole moment. We know the fact that the concept of dipole moment was introduced by the scientist Peter Dipole, and the unit is also his name, that is Dipole, and 1 Dipole is equal to 3.34 into 10 raised to minus 30 coulomb meter. It is also equal to 10 raised to minus 18 ESU centimeter. You should keep some important points here. This unit and their conversion is essential to solve some problems related to dipole moment, and you have to keep these two numerical values with you. And in the first case, 1 Dipole is equal to 3.34 into 10 raised to minus 30 coulomb meter. You know the dipole moment mu is equal to Q into D. The unit of charge Q is coulombs and the distance is meter. Therefore, the unit of dipole moment here is C into M, that is coulomb meter. In other system, you can represent charge in electrostatic units and distance in centimeter, that is associated with the CGS system. The Coulomb meter is in SI system. So, whenever you are representing charge using electrostatic unit and distance by centimeter, then 1 dBi will be equal to 10 raised to minus 18 ESU centimeter. Electrostatic unit into centimeter. So, 1 dBi is equal to 3.34 into 10 raised to minus 30 Coulomb meter, which is the SI unit, and 1 dBi also equal to 10 raised to minus 18 electrostatic unit centimeter. Now, molecules with net dipole moment are said to be polar, which means that they have an asymmetric distribution of charge. So, in a polar molecule, there is an asymmetric distribution of charge. If charge distribution is uniform, then you can call it as a non-polar molecule. For example, HCl is a polar molecule with the net dipole moment value mu is equal to 1.03 dBi. This is the observed dipole moment of the molecule HCl. So, the observed value may have slight variations with the temperature and other external conditions. So, this is approximately the dipole moment value of HCl equal to 1.03 dBi. Now, molecules with no dipole moment are non-polar and there occur symmetric charge distribution. Let us consider the case of Cl2 molecule, chlorine molecule, Cl single bond Cl. Here there is no charge separation because the bond is a non-polar covalent bond. As a result, the charge distribution is symmetric and this molecule is non-polar and this is associated with the zero value of the dipole moment. So, for non-polar molecules, the resultant dipole moment is equal to 0 and for polar molecules, there is a net dipole moment. In the case of Cl2, as we know, the dipole moment is equal to 0. Now, we are discussing another important concept, that is nothing but concept of bond moment. We heard about the concept of dipole moment and we are now focusing on the concept of bond moment. Bond moment simply means in a polyatomic molecule there may be the presence of more than one covalent bonds. You can assign the dipole moment for each and every bonds. In such a situation, the dipole moment is called dipole moment of a bond or it is simply called the bond moment. These are the details. The polyatomic molecules contain many number of bonds between the atoms. Each bond has a definite dipole moment. Each bond has a definite dipole moment and hence makes definite contribution to the overall dipole moment of the molecule. That means, suppose in a molecule, if there are 4 covalent bonds and each bond has some polarity and each bond has some individual dipole moment. These individual dipole moment added vectorally to get the complete dipole moment, or the total dipole moment has a contribution from individual bond dipole moment or bond moment. The dipole moment of a chemical bond is called the bond moment. This is the single word definition of bond moment, or bond moment is the dipole moment of a single chemical bond. It does not depend on, the bond moment does not depend on the nature of the molecule, whether the molecule is bent, linear or having tetrahedral shape or any other shape having centrosymmetry etc. has no relation with the individual bond moment. That is, individual bond moment is totally free from the nature of the molecule. The dipole moment of a molecule is really vectorial sum of individual bond moments present in it. This point I already mentioned. If a molecule is having 4 bonds and each bond has individual dipole moment or bond moment, the vectorial sum of the individual bond moment will lead to overall dipole moment of the molecule. Now, we are discussing a crucial area, that is nothing but factors influencing dipole moment. You know, dipole moment is the measure of resultant polarity of a molecule. It is governed by many factors. We are now focusing on such factors that govern the dipole moment. The first factor is electronegativity difference. You know, a polar molecule is associated with a bond having two atoms with considerable difference in electronegativity. That is, if you are taking HCl, there is electronegativity difference and there is resultant polarity. If you are taking H2 molecule or Cl2 molecule, the participating elements have a similar electronegativity and such bonds are non-polar because the electronegativity difference is 0. So, it should be noted that electronegativity difference has close alignment with the dipole moment. This implies that a greater difference in electronegativity between bonded atoms increase the polarity and increase the dipole moment. For instance, HF has higher dipole moment than the HCl molecule. This is because fluorine is most electronegative than chlorine, leading to greater difference in electronegativity in HF. That means in HF, the participating atoms are hydrogen and fluorine. Their electronegativity difference is very high when compared with the hydrogen and chlorine, which are the participating atoms in HCl molecule. So, higher the electronegativity difference, more will be the polarity and more will be the dipole moment. Now, the second factor that govern dipole moment is here, it is molecular shape. The geometry of the molecule determines if the individual bond dipoles add up to a net dipole moment or cancel it. There may occur some cancellation effect, there may occur some add up effect, etc., that strictly connected to the molecular shape. This I can illustrate by taking another example. This is the situation. You consider the carbon dioxide molecule. Carbon dioxide molecule can be represented as a linear arrangement like this. Here these two bonds are individually polar. Here carbon is partial positive and oxygen is partial negative. Similarly, this oxygen is also partial negative. The direction of the dipole moment bond vector is in this direction and another component bond moment is this. These two vectors mutually cancel each other due to the linear arrangement of this molecule. So, here the net dipole moment mu is equal to 0. Similarly, if I am taking the water molecule which is represented as HOH, it is also a triatomic molecule. Carbon dioxide is a triatomic molecule. Water is also a triatomic molecule. But here there is no vector cancellation effect due to this bend shape. One vector moving like this, another vector moving like this. These two vectors will not cancel each other and there is a resultant vector towards the top direction. And this bend shape provide a dipole moment of 1.84 dBi to the water molecule. So, it is very well clear that molecular shape has a strict connection with the magnitude of the dipole moment. H2O, it is a bent molecule. This part I already mentioned with the help of the diagram. Now we are discussing the concept of bond length and its influence on dipole moment. Long bond distance result in larger dipole moment if the charges remains same. So, if you are considering a short bond length and a longer bond length and assume that the charges on the participating atoms are the same. So, you know the fact that bond length and dipole moment has some close relation. Longer bond distance result in larger dipole moment. This is also clear from the expression for the dipole moment. Dipole moment mu is equal to q into d. If q is a constant, with increase in value of d, d represents the bond length. If increase in value of d is there, then dipole moment also increases. So, bond length is directly proportional to dipole moment, keeping charges constant. Bond angle is another factor that govern dipole moment. Now the question arises, how bond angle is connected to dipole moment? If M1 and M2 are the bond moments and alpha is the angle between these two bonds, then the net dipole moment mu can be calculated by the expression mu is equal to under root m1 square plus m2 square plus 2 m1 m2 cos alpha. Here alpha represents the angle between two bonds whose bond moment are M1 and M2 respectively. So, this is the present situation. For example, in water molecule, there are two OH bonds and these two OH bonds has a component dipole moment M1 and M2. Since both are hydrogen atom, in the case of water molecule, M1 is same as M2, that we can illustrate by some other examples. Okay. So, you have to consider the situation like this. In a molecule, there are two bonds, two different bonds, and these two different bonds are separated by an angle alpha, and these two different bonds have two different bond moments, namely M1 and M2. Then the angle between the bonds is governed by the expression mu is equal to under root M1 square plus M2 square plus 2 M1 M2 cos alpha. Once you know M1 and M2 values and resultant dipole moment value, you can evaluate the alpha, that is the bond angle. So, bond angle has some close connection with the dipole moment. This factor we can consider more detail in coming modules. Now, we are focusing on another aspect, dipole moment and percentage of ionic character. You know the fact that dipole moment is a measure of resultant polarity of a molecule. So, if there is resultant polarity, there may occur some ionic character. If polarity is 0, the ionic character will be 0. So, dipole moment has some close connection with the percentage of ionic character. Now, we are discussing the mutual connection between dipole moment and percentage of ionic character. Through this discussion, we will establish the fact that we can calculate percentage of ionic character from dipole moment measurements. We can now enter into the details. The percentage of ionic character of a bond can be calculated from the dipole moment. This point is very relevant. The greater the ionic character of a bond, the greater the charge separation and larger will be the dipole moment. So, there is a direct relationship between ionic character and dipole moment. The percentage of ionic character is calculated by comparing the observed dipole moment to the dipole moment if the bond were 100% ionic. That is, you can calculate percentage of ionic character from dipole moment. The percentage of ionic character of a bond is obtained from the ratio of observed dipole moment to the dipole moment for complete electron transfer. This is the expression for determining percentage of ionic character from dipole moment measurements. See, percentage of ionic character equal to mu observed divided by mu ionic multiplied with 100. Here the question arises, what is mu observed? Mu observed stands for the measured or experimental dipole moment of a molecule. And what is mu ionic? It is called theoretical dipole moment for 100% ionic bond. That is, you have to assume your molecule as 100% ionic in determining the value of mu ionic. For example, you are provided with the HCl molecule. It is having a present dipole moment of 1.03 and that is the observed dipole moment. Suppose if HCl acts as H plus and Cl minus, then there will be an ionic dipole moment, say the mu ionic. For HCl, it can be calculated from the bond length and it is equal to 6.9. So, you can calculate the percentage of ionic character of HCl by using the expression mu observed divided by mu ionic multiplied with 100. We can illustrate this concept by taking some problems. This is first example. The observed dipole moment of hydrogen fluoride molecule is 1.98 dBi. The dipole moment for its ionic structure, that is here we treat HF as H plus and F minus. It is now converted to completely ionic. So, the dipole moment when HF acts as a perfect ionic molecule, it will be 4.4 dBi. The question is, what will be the percentage of ionic character of HF? You are familiar with this question, and here two parameters are given. First one, observed dipole moment, which is equal to 1.98 dBi, and the dipole moment for 100% ionic HF, that is also given, it is equal to 4.4 dBi. Now you can use this expression for calculating the percentage of ionic character. Percentage of ionic character is equal to mu observed divided by mu ionic multiplied with 100. So, the percentage of ionic character in the present problem is 1.98, that is the observed dipole moment, divided by 4.4, which is the dipole moment for 100% ionic molecule which is formed due to complete electron transfer. So, you have to multiply with 100 to obtain it as a percentage, and the result is equal to 45%. So, for HF molecule, the percentage of ionic character as determined from dipole moment measurements equal to 45%. This is another example which relates dipole moment and percentage of ionic character. The question is, the experimental dipole moment of HCl is 1.03 dBi. The bond length of HCl is 127 picometer. Calculate the percentage of ionic character. See, in this question, mu observed is given and mu for ionic bond is not given directly. Instead of that, they provide the bond length of HCl molecule, which is equal to 127 picometer. But we know percentage of ionic character is equal to mu observed divided by mu for 100% ionic compound multiplied with 100. So, in order to solve this problem by using this equation, we have to first compute mu ionic, that is the dipole moment for 100% ionic HCl. That is, all HCl molecule exist as H plus and Cl minus. We should get the dipole moment for such an arrangement. That is, mu ionic should be calculated from this bond length. So, we have to proceed in a systematic way to get to mu ionic. We already have mu observed, then you have to use the equation for getting the percentage of ionic character. So, mu theoretical is also equal to Q into D. Mu theoretical or mu for 100% ionic bond, this is mu theoretical, it is another notation. Mu theoretical is same as mu ionic. Both dipole moment, mu theoretical and mu ionic are same. Mu theoretical or mu ionic is equal to Q into D, and you know, when complete electron transfer occurs, HCl is converted to H plus and Cl minus. So, here there is a complete negative charge and here there is a complete positive charge. So, 1 unit positive charge and 1 unit negative charge on hydrogen and chlorine respectively. So, the magnitude of the charge is charge of electron. You know, the charge of electron is 1.602 into 10 raised to minus 19 coulombs, or simply you can take it as 1.6 into 10 raised to minus 19 coulombs. And the distance between them is already given, that is the bond length, that is equal to 127 picometer, which is 1.27 into 10 raised to minus 10 meter. On simplification, you will get to mu theoretical, which is same as mu ionic. Mu ionic means the dipole moment for 100% ionic compound equal to 2.032 into 10 raised to minus 29 coulomb meter. So, the given dipole moment is, the calculated dipole moment is 1.03 dBi and mu theoretically is in coulomb meter. So, we have to make the units similar. So, I have to convert this coulomb meter into dBi. For that purpose, we have to use the relation, we have to use the conversion factor. We previously mentioned about the conversion factor that 1 dBi is equal to 3.34 into 10 raised to minus 30 coulomb meter. So, mu theoretical can be converted to units of dBi by using this equation. This is the present value 2.032 into 10 raised to minus 29, the whole divided by 3.3 into 10 raised to minus 30. Then you are getting the value in dBi units and it is equal to 6.09 dBi. So, it is very well clear that for HCl molecule, the observed dipole moment is 1.03 dBi and mu ionic or mu theoretical will be equal to 6.09 dBi. Now, you have to divide and multiply with 100 to get to the percentage of ionic character, and percentage of ionic character is equal to mu observed divided by mu for ionic, mu for theoretical multiplied with 100. So, the result is 1.03 by 6.09 into 100 and the answer is 16.9 percentage. So, HCl molecule shows a percentage of ionic character of nearly 17 percentage. Now, we are discussing applications of dipole moment. Applications of dipole moment are enormous. We can have now a list of applications that can be provided by the dipole moment measurements. The first application is determining bond polarity. The dipole moment of a molecule is proportional to the polarity of a bond. The second promising application of dipole moment is determination of molecular symmetry or shape of the molecule. A molecule with a net dipole moment is asymmetrical because there is asymmetrical charge distribution, while a molecule with zero net dipole moment is symmetrical. This is because the charge distribution is symmetrical. Now, another application is distinguishing between isomers. You are familiar with the fact that in organic chemistry there are cis isomers and trans isomers. This measurement of dipole moment enable determination of the isomerism, determination of the stereoisomers. We can determine whether the compound is in cis form or trans form is made possible by dipole moment measurements. Dipole moments can be used to distinguish between cis and trans isomers, ortho, meta and para isomers in substituted benzenes. Calculating ionic character is another promising application of dipole moment. Dipole moment data can be used to calculate the percentage of ionic character of covalent bond or ionic molecules. This matter we have discussed just previously. We know the expression for percentage of ionic character from dipole moment measurements. Here the equation is percentage of ionic character is equal to mu observed divided by mu ionic or mu theoretical, both are same, mu observed divided by mu ionic multiplied with 100. Here mu observed is the experimental or observed value of the dipole moment, and mu ionic, which is same as mu theoretical, which is the dipole moment for a molecule if the given molecule assumes 100% ionic character. So, percentage of ionic character can be calculated from dipole moment measurements. Now, bond angle determination. It is possible to determine the bond angle between two bonds with the help of dipole moment measurements. It is not possible in all kind of molecules, but there are special examples. We can exemplify this concept with several examples, especially we will discuss that concept in coming modules. Now, we are discussing it for the sake of convenience and for the sake of discussing applications of the dipole moment measurements. So, bond angle determination. If M1 and M2 are bond moments and alpha is the angle between their directions, then the resultant dipole moment mu is given by this expression. Mu is equal to under root m1 square plus m2 square plus 2 m1 m2 cos alpha. This situation I can represent with the help of a simple illustration. You consider a molecule that is nothing but ABC. ABC is a molecule, AB, where A is the central atom. This is one bond, this is the second bond. You imagine both the bonds are polar and the bond moment of the first bond is M1 and bond moment of the second bond is marked as M2, and if there is an angle between these two bonds which is marked as alpha, then the resultant net dipole moment of this molecule, let it be equal to mu, then mu is related to the component bond moments M1 and M2 and the angle alpha by the relation mu is equal to root of M1 square plus M2 square plus 2M1 M2 cos alpha. This concept we can illustrate by taking H2O molecule as an example. In water molecule, there is one central oxygen atom and two peripheral hydrogen atoms, and water molecules assumes a bend shape like this, and it is possible to determine the bond angle in water molecule with the help of this expression. And moreover, you have to keep the fact that two OH bonds are same, therefore the bond moments are also same by using the concept of bond moment which is equal to 1.5, and the resultant dipole moment of water mu is already known to you, that is equal to 1.84 d by, that means M1 equal to M2 equal to 1.5 and resultant dipole moment mu is equal to 1.84 d by. By using these considerations and the equation, it is possible to compute the bond angle between two bonds, that is 1.84 is equal to under root 1.5 square plus 1.5 square plus 2 into 1.5 into 1.5 cos alpha. On solving this, you will get to the value of cos alpha. From that, you can find out the value of alpha, which is again same as the actual bond angle of water molecule, that is 104.5 degree. So, once you know the bond moments and resultant dipole moment, it is possible to calculate the bond angle between two specified bonds. Now, understanding intermolecular forces is another promising application of dipole moment. The dipole moment of a compound is related to the strength of intermolecular forces. Explaining the dissolution of ionic materials in polar solvents like water can also be discussed with the help of dipole moment values. Water molecule can attract both positive and negative ions because of their polarity, and it allows ionic materials to dissolve in water. So, a polar molecule with resultant dipole moment is highly soluble in water. Now, we are discussing this concept and applications of dipole moment with some examples, or we are going to discuss the application of dipole moment, especially in determining the geometry of molecules with some examples. The mu and geometry of molecules are mutually related. Here we have some examples. First point is very relevant. All the monoatomic molecules are symmetrical because their dipole moment is 0. Monoatomic molecules are exemplified by the noble gases. All the noble gases are monoatomic molecules. Noble gases like helium, neon, argon, krypton, xenon, radon, and finally the recent noble gas organozone. All these are monoatomic molecules or monoatomic gases, and these molecules cannot have a bond between other atoms or any other atoms, that is, they are individually existing. Since there is no bond, there is no bond moment and there is no dipole moment. That means all the monoatomic molecules are symmetrical because their dipole moment is equal to 0. So, all the molecules, all the monoatomic molecules have 0 dipole moment, and it is a very important observation regarding monoatomic gases like noble gases. Now we are discussing about homonuclear diatomic molecules. What do you mean by the term homonuclear diatomic molecules? A diatomic molecule with the two participating atoms are same, then you can call it as a homonuclear diatomic molecule. There are several examples like N2O2, F2, halogens, etc. Look, this Cl single bond Cl, this is chlorine, nitrogen triple bond nitrogen, oxygen double bond oxygen. Another example, hydrogen single bond hydrogen. All these molecules are examples for homonuclear diatomic molecules. You know the fact that in these homonuclear diatomic molecules, the participating atoms are same and hence there is symmetrical charge distribution. So there is no charge separation. If there is no charge separation, Q will be equal to 0 and hence you know dipole moment is Q into D. If charge separation is 0, then dipole moment will be 0. This implies the fact that all homonuclear diatomic molecules are linear as well as these are having 0 dipole moment. Now we are discussing heteronuclear diatomic molecules. Heteronuclear diatomic molecules are molecules where there is a bond and the participating atoms in the bonds are different. For example, if you are taking the molecule HCl, this provides a nice example for a heteronuclear diatomic molecule. So, in the case of HCl molecule, there is electronegativity difference. So, hydrogen acquires a partial positive charge, chlorine acquires a partial negative charge, and hence there is polarity, there is charge separation, and hence there is net dipole moment. So, in this situation, the dipole moment value is equal to 1.03 dpi. And the direction of the dipole moment is from positive to negative end of the dipole as shown here. Similarly, I can take another hydrogen halide, that is HF molecule. In HF molecule, fluorine is partial negative, hydrogen is partial positive and fluorine is partial negative, and there is a dipole moment vector like this, and here also there is a dipole moment value, net dipole moment value. In a similar way, we can take several other hydrogen halides like HBr, Hi, etc. Suppose I am taking the molecule HBr, the charge separation is like this, H partial plus and bromine partial minus. Here there is a dipole moment vector which points from H partial plus to Br minus, and here also net dipole moment. In the case of Hi molecule also, it is very well established that there is polarity, there is charge separation, and there is resultant dipole moment. So, from this point, it can be concluded that heteronuclear diatomic molecules are linear molecules, but they associated with the resultant dipole moment. So, all heteronuclear diatomic molecules are having resultant polarity and resultant dipole moment. These are the values of dipole moments of hydrogen halides. The first column represents compounds like HF, HCl, HBr and Hi, and HF is associated with the highest value of the dipole moment, that is equal to 1.91 dpi. Next to that HCl, which is having a dipole moment of 1.03 dpi. HBr is associated with a dipole moment of 0.82 dpi, and Hi is the hydrogen halide with the least dipole moment of 0.38 dpi. So, heteronuclear diatomic molecules are linear and all are associated with some dipole moment. That all about the present module. Have a nice learning experience. Thank you.